Jonathan is now going to talk about 10 steps and tools to produce quality software, which is actually a subject close to my heart since I work in the quality area, performance testing side. And Pi Wars, the last couple of Pi Wars, I've run the Pallant competition for looking at code quality. So it's actually a very important part, should be a very important part of your learning to code, is to keep your code, keep the quality of your code up. So, for Jonathan.
Thank you very much. We'll swap notes afterwards. We'll see what I've done. So yes, my name's Jonathan Pallant. I'm an engineer at a local company, Cambridge Consultants. I've given this talk a few times. Actually, I haven't updated the title at the bottom. Last of this at the Device Developers Conference. So this is a brief introduction to our software process. I've described it as a battle-hardened process. As a company, we get through about 300 projects a year. To do that kind of turnover on projects, you've got to get good at it. That's the best way to get good at things, practice. So this is what we do when we develop software for our customers. So a bit about Cambridge Consultants. We've been around for about 50 years, founded in 1960. We design things for people. People come to us with problems, with things they need, and we help them solve those problems. We're based in Cambridge here, it was Cambridge, Massachusetts. They've just moved over the road, they're now in Boston, Massachusetts. And we've just bought a company called Synapse in Seattle and San Francisco. So we're all over the world now. And we generally specialise in the difficult problems. Makes my life interesting. It's hard to say what we do. We basically do anything, any form of engineering, apart from civil. I don't think anyone's asked us to make a bridge yet, but just about anything else. You may well have products in your house that we've designed, but it's never our name on the box. It's always the customer's name on the box. You've probably heard of our customers. So what do I do? So I'm a principal engineer in our wireless software group, so I generally specialise in wireless things with radios. My background is mainly embedded systems engineering, so it's that weird sort of grey area in between hardware and software. I tend to write a lot of software, but it's at sort of close to the hardware, down at the bottom end. And I have a degree from the University of Warwick in computer systems engineering, which was a fabulous degree. It was half computer science, half electronics, and it was really difficult to schedule because I had to go to all of the computer science lectures and all of the engineering lectures, and it meant they couldn't run the two lectures at the same time for the small group of us, so they cancelled it shortly afterwards. So I understand it's coming back. We need more embedded engineers in the world, and it's an ideal degree. So what am I here for? Well, I want to teach you about a process that works. We do this is what we do, it works. These are tips of the trade, if you like, and perhaps an insight into a large company. We've got hundreds and hundreds of software engineers, so we're not sort of Facebook or Microsoft scale, but it might be an interesting insight into a mid-sized company. I don't apologise for this. This presentation contains opinions, and they are strong opinions. If you disagree, come talk to me afterwards. We'll have a gentlemanly discussion about why I'm right. I'm open to persuasion. As a scientist, you should accept evidence when it's presented. If you've got evidence that something is better, I'll happily improve our process. That's what it's all about. So what do we do when we start a project? It's easy at home if you want to start a project to go, right, first thing we need to do is write some software. Go straight to the keyboard. In a business environment, this inevitably results in disaster. So the first thing you need to do is work out what your customer wants. Customers don't always know what they want. Sometimes they think they know what they want, but that's a key part of the process. If you don't get that right, you're in a lot of trouble. So we need to work out what the customer wants, work out what we need from the customer in terms of their requirements, and work out what we've got in terms of pre-existing technologies. The nice thing about working in a company that does so many disparate things is you can get a guy going, we've got a little piece of a project that we did for someone entirely different, in an entirely different engineering area, but that might be relevant. So then we can start to pull these things together and produce what we need. Quality plan is a key part of that process. it sounds, when I first heard about it, it sounded like it was going to be sort of an ISO approved document that was about that thick. It's not. It's simply about writing down how you're going to run this project. So all the tools I talk about today, you need to document, which ones you're going to do. Maybe you're not going to do some of them. Maybe they're not relevant for your project. You need to tell people, where you're going to get the source code from, what your build environment's like. You don't want to rely on tribal knowledge. You don't want to be running one of those projects where people go, how do I start on your project? I'm new, I'm going to join your project. You go, the only way to find out about this project is to go and ask Steve. And Steve lives in some sort of dungeon in the corner and he's the guardian of all knowledge. That is not a good way to work. So you've got to write it down. We call that a quality plan. So my first tool is, of course, revision control. I mean, it's obvious, isn't it? Everyone uses revision control, surely. That system where you can store your source code and every version is checked in and you can go back to your old versions. Git's a very popular one these days. We called a vendor up. We had some software from them, I think it was predictive text or something. We said, we want this version you gave us a couple of years ago, last time we worked on the project, but we just need a small change. That's all the customer wants, just a small fix, but we want that with a small fix. We can't afford to pick up all the other fixes because it involves doing too much retesting. And they said to me, but sir, you cannot step into the same stream twice. No, I pretty much, that's what revision control is. You very much can go and step in the same stream. You just check out the old one, and apparently this is a surprise to some people. The important thing about revision control is you've got to think about what needs to go in. Linker scripts, tools you use to build your installers. Maybe you've got some DSP code, maybe you've got some FPGA design, maybe you've got some resources like text and icons. It's all got to go in there. You've got to think about how you're going to use your revision control. Maybe you operate what's called a stable trunk. The trunk is sort of your main line of development, and maybe you have a model where anybody should be able to check out trunk at any time, and it will work. And if you want to do something experimental, you do it off in what we call a branch. You do your little experiments, and then put it back on trunk when it works. And maybe you want to work in an environment where trunk is the latest and greatest, and just check in whatever you've got. And if you want to check out trunk, it's a bit of potluck. Might build, might not. There are pros and cons to these approaches. I can't tell you what the right answer is because it depends on your project, but you need to think about it. Semantic versioning. When you number things, you're telling people what version you've got, but it's possible to impart some meaning with this rather than just saying, this is version 2, this is version 3. I can't really tell what's going on there. If I've got version 2 and you're giving me version 3, is that going to work? Is it totally different? When you use semantic versioning, you can give people this information as part of your version number. So we break our version number into 4 parts: major, minor, patch, revision. So that might be 4.1.2.123. The rules are, if you break something, so if someone takes the new version of your stuff and you expect them to have trouble because you've changed something fundamental, you make the major number bigger. If you've added a feature, but everything that was there before should still work, you change the minor number. And if you've just fixed something, you haven't really added any features, then you bump the patch number. And the revision number comes from your source control. So for Subversion, that's a number. For Git, some long, complicated string. So sometimes you have to use third-party tools. Here's an example of a bootloader I was using on a project at work. This is -uboot, the bootloader, and the version number is 2010.06. So that accurately describes when the release was made, but if I wanted to upgrade to 2011.04, it doesn't tell me much about what I should expect from the new version. Versioning things after the year and month they were produced is easy for the creator, but I argue it makes things difficult for people who want to use your product. One of my top tips: your software should know what version it is. The version number it is should be baked into the software. You should be able to run -- version, look at your help page. Makes things much easier when people are filing bugs, because you can go, what version are you running? And they go, hang on a second, click, click, it's this version. It's also useful for checking people have got an official build as opposed to some sort of special build they've crafted themselves with a whole bunch of weird and wacky fixes that I don't know about. Issue tracking. When you give people software, it's inevitably not going to be perfect. They need to tell you what the issues are with it. We use issue tracking for that. You should encourage your users to give you good quality bug reports, which doesn't just apply to software. I know people who run issue trackers on their fridge at home. Just make notes of things that need doing and tick them off. When you get people to give you your issues, make sure you get logs, make sure you get that version information. In your issue tracker, fit it with your version plan. So you should know your roadmap for your product, and you should be able to say, this issue I'm going to get fixed in this version, whereas this fix is going to take a little bit longer. This will be in the version after. And then when people ask you for new features, you can tie that in as well. It should be tied into your revision control system. Our revision control system and our issue tracker, which is Jira, they talk to each other. So if I put the Jira IDs in the commit messages, then it gets picked out. You can do the same sort of thing on GitHub. That's a picture of our issue tracker. For those of you who know Atlassian Jira, that is a particularly old version. I'm working on it. I think we're on version 4, up to version 6 or so. But it's functional. Continuous integration. So this is a big one. Continuous integration is about continually building the source code that's in your repository so you know what state it's in, whether it's passing its tests, whether it actually builds. It's so important. When you're a professional software developer, you basically live continuous integration. Back in 2009, when I started at CamJam Consultants, there were some continuous integration systems around, but they weren't that great. They didn't fit our model. I could be working on 4 different projects at once, and a person who has permission to see project A doesn't necessarily have permission to see project B. So we needed quite a strict sort of permission system. So we wrote a continuous integration system from scratch. About 4 engineers, took us a couple of years, on and off, sort of in the little gaps between projects. We call it Smoky. And this is how it looks. So you can see where I put my tasks. So a task is like a recipe, it's a thing I wanted to do, and then the tasks get turned into jobs. And every time we change the source code, a job is fired off for all of the relevant tasks. This system builds everything from 4K of PIC firmware for a tiny embedded device to a full 14-blade 5 nines telecom chassis. It will compile the code, it will install the code onto remote hardware and run through regression tests. So that means the engineers can click commit, and then this system fires up, build the software, run all the unit tests, all the regression tests, install all the hardware. It's so important. Very observant, I'm not sure how well you can see. There is a task on there that says compile Smoky. Smoky, of course, compiles itself every time there's an update. Which is actually an interesting problem when I come to update Smoky. So I'll log into the server and I'll shut the processes down, and I'll go, right, I need the installation tarball. So I'll fire up Smoky to download the installation tarball, the Smoky that I've just turned off in order to upgrade it. Remember to download the install package before I turn it on. Build environment. How many people in the work environment have said this? Builds fine on my machine. Must be your problem. I used to say that. Or this one, this was a good one. The first build is a bit tricky, but once you've got the first build going and you've got all the dependencies, it's fine after that. Awful. So we fixed this with virtual machine environments. So if you heard the previous talk, Docker containers are sort of an evolution of that. They're sort of a lightweight environment. The reason we like virtual machine environments is because we have weird and esoteric tools that only run on Windows XP or various flavors of Linux. So we can package it all together. It doesn't matter if the developer's running Windows or Linux. They just download the VM. It's got all the tools inside. And for your continuous integration, that means it's repeatable. You get a fresh copy of the virtual machine for every build. There's no chance that there are some little artifacts left over from the previous build, because when the build's done, throw it all in the bin, get a fresh one next time. Our virtual machine system, we use VMware. There are lots of others available. There are some open source ones, CamJam, Zen. The key thing is, the VM that we use on the continuous integration system to build the source code that we ship to the customer is the same VM that developers use all day long, building the software on their desktop. So that's key. So you know that if it builds on your desktop, it's going to build when you hit commit. Also means you can switch projects easily. You know, when we're working on this many projects, we go doing the user interface code for a mobile handset, and I'm going to switch to doing, I don't know, a DECT radio microphone system. It's fine. Close that VM, download the VM with the DECT compile tools in. Off we go. There are other modern tools you can use like Vagrant to get you set up, so you can look into that. So this is the virtual machine page on Smoky. The terminology was a bit tricky. We sort of tried a few terms. Eventually we settled on a frozen virtual machine is like the template. That's the one that lives in the freezer, and when you want to do a build, it clones the virtual machine. You see clone virtual machines at the bottom. That's what it does the building. Does the build in a clone, and it throws the clone away at the end. And then we wanted this idea, well, if you need to install some new software, you need to take your frozen VM, and we call it defrosting it. So we defrost the VM, install the extra packages or whatever, the compiler upgrade, and then you can freeze it again. Defrosting a VM is relatively expensive, because it's got to take the 40 gigabyte file and copy it. Clone is really cheap, because it can reference the parent. The frozen VMs can never change, they exist forevermore. So that means these clones can reference the frozen parent VM, and they're really quick to spin up. Another one of my top tips: there is a difference between building the code and running the code. So maybe you need, I don't know, some kind of flash tool to install it on the hardware. Maybe you need an installer. Can you script your installer? So don't just think that because your code is built, you're finished. Think about how users are going to run the code when they get it. Scriptable installers are really useful, because if you don't have a scriptable installer, you can't automatically test your installer. Code quality. This is a one I'm really big on. Code templates. Code templates are so important. Here's an example of a code template. We use it going to consultants. So we've got a header block at the top, sort of author, copyright information, the description, explain what's going on. This happens to be C code, so we split our hash includes into 3 separate areas. We've got system-wide, we've got our interface headers, we've got our local headers. We break out your public data, private defines, private data types, private function prototypes. It's all split out, and it means when you go to find something, you get used to these sort of visual markers. They're like white lines in the road. Nobody looks at the white lines, but they're there to sort of steer you in the right direction. That's how I see these code blocks. The most important one at the bottom, end of file. If I read a source code file now, and it doesn't have end of file at the bottom, panic. I've got all of it. Is this it? Or is there more that I'm missing? Maybe my download failed halfway through. I have an end of file block in there, just to give you that reassurance that, yeah, you've got all of it. Code reviews, another really important part of code quality. You've got to get your engineers together. You've got to get them talking about the software. It's not about people saying, "Ah, you are wrong. You know, here are the rules, and you haven't followed them." It's about having that discussion, and it's about mutually agreeing the standards. Another top tip: if you're using revision control and you're using a template, if you're using a system like Subversion, where it understands the concept of copies, copy your template, SVN copy template.c to library.c, and then your first diff will remove all of the template and you can see the code you've added. If you just copy and paste the template in, that first diff's got everything in. It's useful. Static analysis. So this is a tool which looks at your source code and it picks its way through much better than the compiler can. It takes a lot longer than a compiler, but it can work out perhaps if you're going to go off the end of an array, or if you're going to recurse too many times, or if you've allocated some memory and you've lost the memory somewhere. We use a tool called Coverity, but it's really important you use this kind of tool and you turn it on from the start. Turn all your compiler warnings up to maximum. You don't tolerate any of this nonsense. Get it on as early as you can, and look at it. If it's telling you there's problems in your code, you've got to fix them. Ideally, it would be nice to fix the errors before you put them in Subversion, but Coverity works the other way around. Oh. The developers all run the debug version, and they fix it all. They go, yeah, this is good, and then they pull the switch that says, yeah, optimize. Switch it to release mode, build it, and ship it. I would argue that's not a good idea. The developers should be working every day with the version the customers are using. Otherwise, the customers will report bugs that you developers don't see because they're in release mode, not in debug mode. You must have found Heisenbugs, those bugs that are there until you add the debug code to work out where they are, and then they disappear. See me afterwards and I'll tell you a horrible one about pointer offsets for a DSP load. Turned out to be a compiler bug. If you can't debug it, you can't test it. If you can't test it, I would argue you shouldn't be shipping it. So the tip is, put enough debug code in your release build. You could switch it on with a software flag maybe. Maybe it just ticks away in the background and goes nowhere. But you should be able to debug your release build. Another key one, interfaces. You've got two modules talking to each other. You need to agree how they're going to talk, especially if you've got different developers working on each side. We put this into what we call an interface control document. It explains the what and the how, whereas your system specification explains the why. But it means that you can agree, and when you get together to bring your two modules together, you can have a discussion about, well, I'm sending you this message, and I'm sending you this message back, and I don't understand your message. Well, now we can go back to the interface control document and work out what's going on here. Even better, you can use systems where you could describe your interfaces in some sort of machine language, and then you can generate your code and your documentation from a common source. Sometimes you can generate your documentation from the source code. You've got a language that has those kind of features, but that's really important because it resolves those ambiguities. It's impossible for the documentation to not match the code because they come from the same origin. So yeah, it's sort of Word document we produce, full of tables, explains all the fields, byte alignment of everything. Very important to specify endianness. Obviously everything should be big endian, but you do come across modules that people cheat and they just use whatever their machine does. You've got to be consistent about sizes. So the world's third most popular chip by instruction set is probably the one Cambridge Consultants designed in-house. We gave it to our spin-out. You might have heard of them, Bluetooth company called CSR. They put one or two of our ZAP processor cores in every one of their Bluetooth chips. So there's billions of these chips around. They happen to use a 16-bit byte. So we're a bit touchy about the word byte, because as far as we're concerned, it's ambiguous. It's 8 bits, say octet. But that's the kind of thing your interface needs to resolve. Getting on to testing. There's 3 parts to testing. The first part is your unit test. So you unit test individual modules, you test them in isolation, you do it automated, on commit, run it on your desktop as well. You get some code coverage, so you check which lines of the code were exercised as part of your test. And if you're not covering, a majority of them, maybe you need some more unit tests. That's the sort of code coverage we report, we generate on Smoky. Hopefully the red ones aren't my code, down to 70%. Yeah, it's not great. There's some good ones at the bottom, the Read Solid encoder and ARC4. We're pretty satisfied those are going to work. It's impossible. It's hard to get it good, and it's impossible to cover everything because it's going to take you a long time. But you should make sure you're covering the areas of high risk. Those algorithms you think this is a little bit tricky. Make sure you've got some unit tests when you're covering it. Regression test is your next step up. So regression test is when you've got your program talking to a simulator. So it's wrapped in a fake environment. And it's automated, you run it on commit. I said earlier about that telco hardware. We can load that onto the chassis, it's off onto the chassis, and then that connects up to virtual telephony devices and a virtual satellite system. And it's the final product, but it's sort of running it's like it's in the Matrix. it's in this virtual environment, and that means you can exercise it. Like you do on the Matrix, you can break various rules, which is giving thorough exercising. We have our own in-house test system, lots of passes, that's what we want to see. The final one is the system test. So here you've got to plug it into the real world, and it's probably quite tricky to automate this sort of thing. So you're going to have to get some testers involved. So, this is what we covered. We talked about revision control, we talked about semantic versioning, major minor patch system, tracking your issues, building your software in continuous integration and how important that is, living in the continuous integration environment. We talked about getting your repeatable build environments. We use virtual machines, there are other tools available. We talked about the code templates and the code reviews, really important things to improve your code quality. We talked about doing static analysis. We talked about making sure you don't build debug all day long and then ship release. And it's about getting that balance from debug features in release mode. We talked about nailing down your interfaces. And we talked about our three sorts of tests: unit test, regression test, and system test. And I'll leave you with a quote from one of my professors at the University of Warwick. He said, if you aim for perfection, you'll probably hit the tolerances, and that's all right. If you aim for the tolerances, if you aim to produce something that's okay, you'll miss. So aim for perfection, see how many of these you do on your project, and come and talk to me afterwards. Thank you very much.
Are there any questions?
When you're working with multiple clients, how does the intellectual property of the code work? Do you own it, or do the individual clients own it? Can you use code that you develop for one client for another client? How does all that work? Or does it vary?
That's a discussion we have with every customer. Customers have to understand there is value in us being able to reuse code we've written for them in what we call a non-competing area, because in exchange they get to use code we've developed in a non-competing area for another customer. So they have to understand there's that trade.
So it's only with non-competing. So if you're building something for one manufacturer's mobile handset, you couldn't use that code in another manufacturer's mobile handset?
I think that would be bad for business.
Andrew?
You mentioned you do builds inside VMs.
Mm-hmm.
Does that cause problems with commercial IDEs?
So, very often, take Visual Studio as an example. Microsoft have just released the complete tool chain underneath Visual Studio as a standalone installer. And they've made that so you don't need a license to use it. So you need your MSDN license to use Visual Studio, but for continuous integration you can get the tool separately. Very often we're doing builds on Linux and we're just using GCC and Make. Sometimes there are proprietary IDs, sometimes they have license restrictions. If that happens, we'll use a floating network license, and the continuous integration system will grab the license, do the build and release the license, and we can tell it, in this case, only do one build at a time. You know, if it's a standard build, spin up as many as you want. Sometimes you get a developer that goes commit, 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 and then it spills up a build for each. But if you're using a license, you can slow that down.
Do you have tools for checking things like GPL pollution?
That's an interesting one. We try to be rigorous about how we organise our code. And if we're using third-party code, whether it's under the GPL license or another open source license, or whether it's proprietary code, you know, we might be using a proprietary RTOS for mental graphics, for example, or we use the U-boot bootloader, and that's under the GPL. Whatever the license of code is that we haven't written, we have to know about that. So it's always in the headers, and we try and produce a software release note that details the copyright. If you're using BSD code, that's fine, you can use it in your proprietary product. But it does say you have to specify the author and the copyright statement. It says you can use this if you copy these 3 blocks. So we have to be aware of that for all sorts of licenses. But there's no, we don't use a specific tool to do that.
Jonathan, you guys looked at Go, producing something like sort of a safe alternative to C.
So some people at work are looking at Erlang. I know some people at work are looking at Go. The other presentation I have on here is a presentation in Rust, because I am completely addicted to Rust, and it solves a lot of those tricky code quality issues. We'll see. Maybe I'll come back next time and talk about Rust and Raspberry Pi.
Okay. Is that everything? Thank you very much.
Thank you.